All right, so hello everyone. My name is Brian. I'm the Department Chair of Mathematics and Statistics at Okanagan College. And in this particular video, we're going to take a look at matrix systems, specifically ones where we might be working in modular arithmetic, and see when these matrices might have inverses and potentially use them to solve some bigger problems, I guess, involving mod arithmetic. I am a department chair, it is true. Yes, you heard it directly from me. Okay, so the first thing we want to do is start with a definition. So let's suppose we have a couple of matrices. So capital S and T. Let's suppose they are n by n matrices. I'm going to work with square matrices here. We say that S, capital S, is congruent to capital T mod n. Okay, so again, kind of assuming here that n is a positive integer, if all of the entries in S are congruent to the corresponding entries in T mod n. Okay, so this has to be true component by component or entry by entry. Okay, so that's the big kind of key idea here. So if you want to know what this looks like with maybe a 2 by 2 matrix, it's going to look something like this. So let's say we have capital S. We have 8, 4, 9, and 7. And we have capital T, which is 13, 4, 14, and 12. We can show that these are congruent mod 5. So S mod 5 would look something like this. We just go through entry by entry, look at the remainder after doing division by 5, and update that matrix. So our 8 would turn into a 3, it has 3 remainder. Our 4 would stay the same. Our 9 would have remainder of 4, and our 7 would have remainder of 2. Excuse me. And similarly, if we do T mod 5, we could take a look at the remainders we have mod 5. So 13, 10 goes into there, leaving us with a remainder of 3. 4 stays the same. And again, I can look at the 14 and the 10. I can remove 10 from each of those to get remainder of 4, remainder of 2. So I can see that these two things are indeed equivalent mod 5. So S is congruent to T mod 5 because all of their remainders upon division by 5 are the same. What, lecture 8 on the elements YouTube you need to watch soon? Literally have FOMO? Okay. Do it. I don't even know what's lecture 8. Is that the last lecture that we did with Sasha? Sasha and Slim? So we're interested if matrices are going to be invertible in the particular mod that we're working with. And again, it's not going to be super obvious why this is important today, but if we are going to be working with matrix systems and cryptography a couple modules from now, this particular property is going to be helpful for us to be able to undo an action. So if I'm trying to encode something using a matrix, if that matrix doesn't have an inverse, I'm not going to be able to decode the thing that I've sent to the individual. So it is going to be a little bit of an important building block piece that we need for the future. So let's take a look at a theorem. I think this is the theorem that's going to guarantee kind of what things are going to look like. So let's suppose we have capital S. So suppose we have an n by n matrix with integer entries. Let's take a positive integer m. Such that when we take the GCD of the determinant of our matrix and m, we get 1. You'll see why we need that in a hot second. So if we have all of that, then we can guarantee a couple of things. So then the inverse of S, right? So the inverse matrix of S is D inverse adjoint S. That's our inverse. Now, what is this D inverse? D inverse is equivalent to the determinant of S inverted mod M. Okay, so maybe you can kind of now see, okay, why did I need the GCD of these things to be 1? Because the GCD of these things being 1 guarantees that I should be able to invert the determinant of S, right? Mod M. So that's why that's important. Okay, so I want to go ahead and prove this. And then we'll take a look at some examples so you can see how to work with this formula. The formula is very similar to what we would expect it to be. What's the formula for regular matrices? I think it's like A inverse is equal to 1 over det A times the adjoint of A, right? So it's a very similar formula that we would see from linear algebra. The only difference is this D inverse, instead of dividing by the determinant of S, we need to think about what's the congruence class that represents the inverse of this value that we get, mod M. So that's the only big difference, is we're just converting this 1 over det A into something that works in the modular arithmetic world. Yep, Ryan, you're exactly right. So we want that det S to have exactly one solution, otherwise it doesn't make sense to have an inverse. So the GCD guarantees not only that there's an invertible element, but there's only one, right? There's only one solution to the problem. Yeah, exactly. Okay, I am going to actually just go through the proof of this one, relatively quickly. I don't want to spend a lot of time here. But a couple important points here, right? So this idea that the GCD of the determinant of S and M being equal to 1, exactly like Ryan said, this guarantees not only that it's invertible, but we have like a unique element that's going to do the work for us. Okay, so all that work we did with the kind of linear congruences before we took our break, we're using that right here. Okay, so with that said, let's go ahead and let D inverse actually be the thing that we want it to be. So we're going to take the determinant of S, and we're going to be looking for that invertible element mod M. Okay, so let's take that. So what do we need to do? We need to prove to ourselves or convince ourselves that S times S inverse is the identity matrix. Right, so we're going to try to show that S times S inverse is equal to S inverse times S, which is the identity mod M. So let's go ahead and take a look at what does this multiplication do. Well, this multiplication is S times, we have our candidate for S inverse, it's D inverse adjoint S. And we have our candidate for D inverse. So this is really S times det S inverse adjoint S. Of course, this is all mod M as well. So there is one piece of information that we do need to pull in, and that is the following. If I am working in inverse world, like this, so we know that A inverse is typically 1 over det A.
Have you ever had a dream that
times the adjoint of A.
you had you want?
Stop it, lil bro. Easy as pie.
There you go, Ryan. You can have a QED for that. So, not a commonly used equation, but there is an equation, like if I do some rearranging here, I do get that the determinant of A times A inverse is equal to the adjoint of A. And if I multiply both sides by A, capital A, then I get that the determinant of A times the identity matrix is the adjoint of A times A. And I think this will work in any order. So, and specifically, I'm going to use this order, I guess. I'm going to have A times adjoint A equal to the determinant of A times I. So if I take A and I multiply by its adjoint, I always get an identity matrix. Well, I get a matrix where the determinant value actually lies on the main diagonal and everything else is 0. So it's a very odd property of A times the adjoint, but it's the thing that helps us actually try to figure out what the formula for the inverse is. So if you ever take a linear algebra class, I usually explore this quite a bit because this is the fundamental equation that we need in order to figure out the candidate for the inverse. So just kind of keep that in the back of your mind here. We're going to need to use that right away. Okay. So back to what we have over here in black. This det S inverse is just a number, mod n. So I can move this number out front, and that's not going to affect the overall equation. I do need to maybe, in this case, just be mindful of the order of my matrices. So we'll make sure that S comes first, followed by the adjoint. Here, then, we can use that S times the adjoint of S is equal to the determinant of S times the identity matrix. So I'm going to use that property we talked about here in green. So now I have the determinant of S times its corresponding inverse mod M. That's just 1. So I'm left here with just the identity matrix. And of course, all of these computations, again, have been taken mod M. So that's really nice. You can do the same thing in the other direction. I'm not going to prove it, but that hopefully gives you an idea of we have some of this firepower from linear algebra. Now we know kind of how to work with inverses with linear congruences, put them together, and we have a formula for how to find a matrix inverse modulo M. So that was a whole bunch of blah, blah, blah. So let's go ahead and take a look at an example. Let's consider the following set of equations. X plus 2y plus 3z is equal to or equivalent to 1 mod 7. X plus 3y plus 5z is equivalent to 1 mod 7. And x plus 4y plus 6z is equivalent to 1 mod 7. How in the world could we potentially solve for x, y, and z? It seems a little bit wild to me. It seems like this is going to be a little bit unruly because we're working with mod 7, right? But it's not too bad. First thing we want to do is just get this set up in matrix form. So what we want is we want Sx congruent to T mod 7 in our case, mod M. So I need to do a multiplication, and I need to have the kind of coefficient vector over on the right-hand side. So it's the same setup as what we had before. This capital X is going to take care of my variables, x, y, and z. This capital T is going to take care of my constant terms. And this capital S is going to be the coefficient matrix. So 1, 2, 3, 1, 3, 5, 1, 4, 6. Okay, so these are our candidates for S, X, and T. So what we want to do is we want to see if is it possible to find an inverse for X. If it is, then we can probably just take that inverse, multiply on the right-hand side by 1, 1, 1, and then we get to some kind of solution to our problem. So our question is this invertible? Well, what do we need? So let's go back and just kind of see what we need. So the theorem says if the determinant of our matrix and M have a GCD of 1, then there's a formula I can use to actually calculate capital S inverse. So the first thing we need to do is calculate the determinant of this capital S, and then check to see if it's coprime with 7. So what is the determinant of S? Well, there's a bunch of different ways to do this. I usually do the lazy way with the 3 by 3. So I'll take my 3 by 3, I will attach or append the first two columns, and then I'll start just kind of doing the weave method, or I think I always call it the weave method. So 1 times 3 times 6, 18, 2 times 5 times 1, 10, 3 times 1 times 4, 12. And then I have to go backwards as well. So I have to do 3 of these. So 2 times 1 times 6 would give me a negative 12. I have 1 times 5 times 4, and negative 20. And then a 3, 3, and 1, so negative 9. So let's go ahead and simplify that. So the 12s cancel. This should be easy to do in my head, but it's been a long afternoon. So let's take those two. Let's subtract 20 and subtract 9. I get negative 1. Now, remember we're working with mod 7, so I can rewrite this as 6 if I want to. Okay, so let's check our GCD. So the GCD of 6 and 7. It happened again, chat. It happened again. Is 1. Why does 6, 7 keep coming up? Why? Why? I wrote these like 3 years ago. Okay, our GCD is 1, so S should have an inverse. What is the inverse of S? Well, the inverse of S is det S inverse times the adjoint of S. So we need to find both of these things mod 7. Okay, it should be relatively easy for us to find the inverse of 6 mod 7 without having to do a lot of work. I mean, I could use the Euclidean algorithm if I wanted to. But this is such a small example, we can probably just do this by thinking. So 6 times what would be equivalent to 1 mod 7? 49. So it's not 1. 6 times 2 is 12. That's not going to give us 1 mod 7. 6 times 3 is 18. That would be 4. 6 times 4 is 24. 6 times 5 is 30. We're getting closer. It's 6 times 6 that we need, right? 6 times 6 is 36, which would be equivalent to 1 mod 7. So we could use the Euclidean algorithm here. I'll do a quick little recap of what that might look like. But in some cases, when these numbers are small enough, you can just kind of cycle through your different congruence classes and find the one that works. So if I did do 7, 6, 1, 0, 0, and 1, the Euclidean algorithm would say, well, let's take row 1 and subtract row 2. That will give me 1, 1, and negative 1. And so I get that 1 is equivalent to 7 plus negative 1 times 6. And then we take mod 7 both sides, right? So 1 mod 7 would be equivalent to 0 plus negative 1 times 6. And so we have negative 1 times 6 would be 1 mod 7. So negative 1 is the inverse we're looking for. We already know that that's equivalent to 6. Okay, so when in doubt, you can always use the Euclidean algorithm to get the answer that we want here. Sometimes it's easy just to try to mentally do it. Sometimes it's a little bit faster. So, how do we find the adjoint? That's the other good question. So, if we take our matrix, 1, 3, 5, 1, 4, 6. So that's S, right? What we want to do is we effectively want to create a new matrix where each entry is like a little 2x2 determinant. So maybe I might need to make this a little bit bigger. But the idea is in the first entry, I'm going to kind of remove these. And I'm going to be taking the determinant of 3, 5, 4, 6. That's going to be entry 1. And then entry 2 is going to be the negative of what's left over. So 1, 5, 1, 6. So I'm going to go ahead and just try to finish off what these like tiny little determinants are going to look like. So this would be like what, 1, 3, 1, 4. And remember, you need to alternate your signs here, right? So it depends on the positioning of where we are. Some of these positions are negative, some of these positions are positive. Okay, so if we're down here, we're kind of getting rid of this and this. So we have 2, 3, 4, 6. 1, 3, 1, 6. And 1, 2, 1, 4. And then for the bottom, we have 2, 3, 3, 5. 1, 3, 1, 5. And 1, 2, 1, 3. Oh, and then I apologize. We have to take the transpose of this once we're done too, I think. Okay, so let's just go ahead and kind of quickly calculate some numbers here. So 18 minus 20 is negative 2. This is 6 take away 5, so that should land us at minus 1. 4 take away 3. 18 take away 12 is 6, right? 6 take away 3. 4 take away 2 is 2. This is 10 take away 9, 5 take away 3 is 2, that's a negative 2, and then 3 take away 2 is 1. Okay, so let's take the transpose of that, and then we'll see, we can get rid of these negative numbers as well, because we're working mod 7. So let's go negative 2, negative 1, 1, negative 6, 3, negative 2, 1, negative 2, 1. And so we have that the adjugate or adjoint of S should be equivalent to, this is 6, 1, 3, 1, 1. What's 2? 2 and 2 plus 7 is 5, right? So this is 5 and 5 and 5. And then 6 plus 7 is 1. Negative 6 plus 7 is 1, right? So this should be equivalent to 1 mod 7. So I just want to double check and make sure that that's what... Oh, I don't have that. Uh... 1, 3, 5, 1, 4, 6. I think that's fine. I might just quickly check this online. So I need an online adjoint calculator for a 3x3 matrix. Yes. Okay, let's put our matrix in. 1, 2, 3. No, 1, 2, 3, 1, 3, 5, 1, 4, 6. Calculate. Okay, so there should be a 0 down here, so I must have done something wrong here. Oh yeah, this is 12 minus 12. That's not 6. Okay, that's where my error is. So this should be a 0, which would make this a 0. So let's make sure that we're happy with this. So negative 2, 0, 1. Yeah. Negative 1, 3, negative 2. Yeah. 1, negative 2, 1. Beautiful. Okay. So I'm happy with that. That means that this becomes a 0, but everything else should be the same. So this is what we should have mod 7. Okay. Happy with that. All right, so we have the two pieces that we need. We have our adjoint and we have the inverse of the determinant. So we'll just put it together. Therefore, S inverse is equal to 6 times this matrix. 5, 0, 1, 6, 3, 5, 1, 5, 1. So let's go ahead and multiply this. We can simplify at mod 7, and then we can go back and solve the original problem to finish off our lesson on mod arithmetic. So 6 times 5 is 30. 0, 6, 36. 18, 30, 6, 30, and 6. Go ahead and simplify mod 7. 21, 28. So this is going to be 2, 0, 6. That should be a 6. 30s become 2s. That's a 6. What does 18 become mod 7? Would be 4, right? And then I need 36 mod 7. We know that's 1. Okay, so that should be our S inverse mod 7. So the original problem was S x congruent to t mod 7. So x should be congruent to S inverse times t mod 7. We know what S inverse looks like. It's 2, 0, 6, 1, 4, 2, 6, 2, 6. Our constant vector was 1, 1, 1, so we just need to do a multiplication here, and that should give us our final answer. Okay, so 2 plus 0 plus 6. We have 1 plus 4 plus 2, 6 plus 2 plus 6. So we have 8, 7, 14. And again, we'll just do a little bit of simplification here. This would be 1 mod 7, 0 mod 7, and 0 mod 7? What? Yeah, I guess that's what I got in my final answer here. So x is equal to 1, y and z are equal to 0. That's the only way to solve this question. So x is equal to 1 mod 7, and y and z are both equal to 0 mod 7. That's the only solution to this particular problem. Does that make sense? Does that make sense? I guess so. I guess that's the easiest solution to the problem, is to just can out y and z. Sure. Okay, it's a solution. It makes sense. There you go. We went through a big process here just to find a very obvious answer. sub 1 equals x, and then you're good to go. You're good to go, man. All right. So there we go. That's going to end your module on modular arithmetic, my friends. I will be back for the next module in your course, which is the Euler phi function, where we'll take a look at the Euler phi or Euler totient function, because there's some really cool properties that we need from that section in order to do some stuff coming up in cryptography as well. So I'll see you then.